NPTEL Live Session of this course. So today I'm going to discuss about the state feedback control for trajectory tracking, because yesterday week we have discussed about the how to design the state feedback controller using pole placement method. There is the Ackermann method as well, and similarity transformation method. Now we will use these techniques to design the state feedback controller using trajectory tracking. So I have a constant, let's say constant trajectory, and we have our wish, or so the wish of the system is to track the constant value. So for that case, what should be the value of the key gain? So we are going to discuss about that, and then we are going to discuss about the state observer, how to find the state observer. As previously we have discussed already that all the parameters of the systems, like it's any system is basically we can define any linear system in a state space form, like x dot equals to ax plus bu and y is equal to cx. Let's say I'm considering the strictly proper system. So in that case, all the so y is basically the measurement value, right? So which is depend on the state x, but it is not possible that we can put sensor everywhere. For full state feedback control, we need all the states, but sometimes it is not possible for the it is not possible for us to measure all the system states from the system, because maybe there is a problem to place a sensor at that position, because it is not if any internal state is required, it is very difficult to place a position place a sensor at that position to measure the internal state. Or maybe it's the sensor's price is very high, or it is not available. So in that case, we need to estimate those state, and to estimate those state we need an observer. So here we are basically talking about the observer, how to design a state feedback state observer. Okay. So the one condition for our case, the one condition is our system uh, uh, has to be observable, right? Our system has to be observable. So if it is not observable, let's say the system is detectable. That means if it is detectable, then the unobservable mode should be stable one. That has to be done. Either all the state either the system is fully observed in case of controllability case. So we when we find out the state feedback control, or when we wish to find out the state feedback control, so our main condition is basically that system should be controllable, right? So in that case, sometime we have seen that our system is not controllable one. Okay, but in such special cases, what another condition we have put? We have put another condition that okay, no problem. If those states are not controllable, are they stable one or not? If the uncontrollable states are stable one, and controllable state and those states are controllable, those states are unstable. Okay, those can be controllable. Then we can say, okay, system is not fully controllable, but system is stabilizable. That means there we can design a feedback controller by which our system reach to the desired position, whether it's a zero or any other positions. Because since we cannot control the we cannot control the stable mode. So we cannot control some states. So we wish that those states should be stable, so that as t tends to infinity, those state goes to the desired position, or zero. So that means our system, there should not, there is no effect of control, because we cannot create any controller, we cannot design any controller for those state which are uncontrollable. For that case, we need those states should be stable, so that those state goes to the desired position by itself. Similar case for observable. the first condition that we need is the strong condition that we need, okay, to design a state observer. That means we are basically estimating the states. So to design a state observer, our first strong condition should be the system should be observable. Okay, that should be the first condition. If the system is observable, then we can design a state observer. You can see how why it is why this condition is required, because in Ackermann's formula in controllability, you can see you have already seen that there is a inverse of controllability matrix. Similarly, you will see here that there is the inverse of observability matrix. So if the observability matrix is full rank, then its inverse is possible, right? In that case, if the system is not fully observable, then we decompose the system in a controllable, observable and unobservable portion, and we check those modes or those states are unobservable, are they stable or not? If they are stable, then we can say the system can be observable. I mean, we can design a state observer. So we will discuss further. So this is the short preview of what we are basically discuss about today. Okay. So let me share my screen first. So first, we are going to discuss about the system. First, I'm going to discuss about the trajectory tracking. Okay. So let's say I have a system. So here. Uh, so in trajectory tracking, in previous class, we have designed. So let's say our system is x dot equals to ax plus bu and y is equal to cx. So this is my system. So in previous class, we basically design a controller where u is equal to minus kx, right? So here we design now. Here we design a controller. We design a controller to track a reference trajectory, right? So our system is should be R. So here, let's say this R is reference. Okay. So basically the system is looking like so this is basically x dot equals to ax plus bu and y is equal to cx. This is the thing. And we design u in that format where we need state and so this is basically the whole scenario, right? So here we are going to discuss about this. So let's say start with an example. So the system is systems transfer function. Right. So systems transfer function is this. So we know this is a so the first thing that we check at steady state where my system will go. Right. So what is the what do you call? What is basically the steady state formula? So this is basically limit t tends to infinity. This transfer function. There is a the final value theorem, which is this yt. This is basically steady state, right? So this thing can be written as limit s tends to 0 s into gs into rs. So what is rs? Rs is the reference input. So I am here. This r is basically the this is rt and its Laplace transform is rs. So for unit step case, what is the steady state value? Limit s tends to 0 s into 1 by s square plus s plus 9 into 1 by s. So it is 1 by 9, that is almost equal to 0.11. So what is the steady state error? So that means 1, because you for unit step it's a 1 and this is 0.11. That means so this is my steady state error. So we need to reduce this error because what is our objective? Our objective is to reduce the steady state error. That means limit at t tends to infinity, our ESS at t should tends to 0 or should equal to 0. So this is basically what is our objective. This is basically our objective, right? So what does that mean? That means we need to design some u so that we need to give an external force so that this happen. So to make this happen, so let's say, and similarly we have the designer have some as designer have some it has some they provided some specification that the desired pole location is s equals to -1, -2. So designer already said that, okay, whatever you do, but this is the pole location that I want. I want that my system pole should lie at -1 and -2, and as well as my steady state my steady state error should reduce, right? So we know that. So this is basically desired characteristic equation, right? So we have to find out the Kc. So using the Ackermann formula, what is Ackermann formula? In previous class, we have seen where the Ackermann's formula. This is the Ackermann's formula, that is E transpose C inverse ADA. This is my Ackermann's formula. Using Ackermann's formula, we have to find out the system. We have to find out the state feedback, right? So for that case, we need to design. We need to find out the controllability matrix. So we have a B matrix. So first of all, we need to design. We need to convert this. So our system is GS equals to 1 by S square plus S plus 9. Therefore, the state space form is, so it is become X dot equals to companion form. Okay. So this should be -9 -1 X plus, they should be 0 1 U. So I'm not going to write the C part because we know we are not required over here. So we have B equals to 0 1.
अरे श्रीराम मला तर हे तर नाव परत त्याला लॉग आउट करू का? कसं करू?
Sorry.
लीव करू का?
Hello. Okay. So Mr. Punit, could you please, I mean, mute your, I think some sound is coming from you, or I don't know. Do you have any questions? If not, then please mute yourself. Hello. Okay.
आता हे ऑफ करायचं असेल तर
So this is B, and now we have to find out AB because we need to find out the controllability matrix. So AB is this. So what we find 1 -1. Okay. So we need to find out the controllability matrix, that is B and AB, because we have to find out the feedback control law. We are basically going to find out the feedback control law using Ackermann's formula. So what is this is 0 1. So this is 0 1, this is 1 -1. So this is C. So we need to find out C inverse as well. So this is C inverse, which is -1. This is C inverse. Okay. So we know that K equals to e to the power E transpose. What is the formula? There is E transpose C inverse alpha 80. E transpose, this is C inverse alpha D A. So in Cayley-Hamilton theorem, we have seen that our system satisfies characteristic equation. So here alpha D A is basically, I'm writing over here, A square plus 3A plus 2. So that is 0, 1 minus 9 minus 1 square plus 3 into 0, 1 minus 9 minus 1 plus 2I is 2002. Okay. So after so it is, so the square is minus 9 minus 1, 9 minus 8 plus 0, 3 minus 27 minus 3 plus 2002. So what we get, it's a minus 7, and then this is 0, 2, this is minus 16, and this is minus 9. I hope I have done nothing wrong. Okay, so you can check that I have done something wrong or not. So this E transpose is 0, 0, sorry, 0, 1, and then inverse is, sorry, and the inverse is 1, 1, 1, 0, 1, 1, 1, 0, and this is minus 7, 2, minus 16, minus 9. So it is 1, 0, minus 7, 2, minus 16, minus 9. So 7 minus 2. So this is my K. So now my system would be, so this was my system x plus bu, right? So now my system is x dot equals to a minus bk u plus br, because I have used that u is equal to minus kx plus r, right? So what is a minus bk? So it is 0, 1 minus 9 minus 1 minus b, b is 0, 1, and k is minus 7, 2 u plus, sorry, this should be x 0, 1 r. So it is 0, 0 minus 7 minus 2 minus 7, 2. So it is 0, 1 minus 2 minus 3 x plus 0, 1 r, right? So now basically if we convert it into a transfer function, so what is the transfer function? Transfer function would be s square plus 3s plus 2, right? So in that case, you will see that if we find out the final value, apply the final value theorem, that is t infinity yt, which is basically limit s tends to 0, s gs rs, which is limit s tends to 0, s square plus 3s plus 2 into 1 by s. So you will see steady state error ESS is equal to basically 0.5. Now previously we started with a steady state error 0.89. We started with a steady state error 0.89. Now we have designed a controller. We have designed a controller using Ackermann formula. You can use any formula, either simulate transform or Ackermann or anything. So using this formula, we have designed a controller which is this, and we have seen that okay, my steady state error is now like this, because there is a there is a designer specification also involved. Like my desired pole should be in that format. It should be in -1 -2. It can't be -1 -1 -1.5. No, it should be -1 -2 because we have to maintain some overshoot something. So that's why this is the design specification. So for that case, we have seen that our steady state error is still there is a steady state error. Still our system using that controller, still our system did not reach to the desired position because our as as you can see, so this is I have my RT is this is my RT, which is unit step function. So I need my system should reach to that position, right? So this is our desire or something like that, either overdamp or something. So if there is any overshoot is there, so in that case, it should be something. Ultimately, our system should reach to the one. But right now, my system does not reach to one position. There is a still steady state error. Let's say some sort of error is like that. So we need to reduce this steady state error, right? For that case, we need some kind of some more specific. We need to design something more. We uh, we know we have a proportional controller, integral controller, and derivative controller. Okay, so the derivative controller basically used to improve the transient response, and the integral controller basically used to improve the steady state response. That means we have to design some integral controller or something another Joe, which basically reduces steady state error. So now let's say instead of u is equal to minus kx plus r, instead of this, so instead of u is equal to minus kx plus r, here we are going to design u is equal to minus kx plus mr. We are basically design, we have already designed this k. We have already designed this k term, and we have considered over here that my m is I. Now we are saying that, okay, do not consider M as an identity matrix. We consider that M, a identity vector or matrix, whatever. Consider M as a different vector or matrix depend upon the number of the states and all those things. So we have to design this M as well. So if whether it is possible to design this M or not. So now we are going to design this part. So basically in this structure, so here, so this is basically the structure as you see. So in this structure, here we have to put something here. We have to put something, a box where M, and this is R. This is the whole thing that we need to add extra, right? So the thing should be, I'm not writing down the whole thing. I'm just, let's say this is x dot equals to ax plus bu. This is the whole system, and y is equal to cx. So I'm getting, or let's say, so this is x, this is c, this is y. So this is b, here u, and here is basically m. This is r, and this is k. Okay. So here M I'm going to design over here. So what should be the system? X dot equals to Ax plus Bu. Now Ax plus B into minus Kx plus Mr, which is now become A minus Bk x plus BMR. Right. So we know steady state means this is a constant term, right? So at steady state, this x dot equals to 0. So what it would be? X equals to A minus Bkx plus BMR. So x equals to minus A minus Bk inverse BMR. So what is my y? Y is equal to Cx. This is C into A minus Bk inverse BMR. We need to design this M, right? So what is our requirement? Limit t tends to infinity, yt equals to rt. This is our requirement. That means ESS, this is yt minus rt. This should be 0, right? So what is yt? So yt is minus c A minus Bk inverse BMR minus R. So this would become C A minus Bk inverse BMR. So this term would be 0 if this term is minus 1, right? So therefore we consider that C A minus Bk inverse Bm is equals to minus 1. Therefore, M equals to minus 1 by C A minus Bk inverse Bm. Now, this is okay for single input CISO system. This is okay for CISO system. But in case of if your system is not CISO, if your system is MIMO system, multi input, multi output system, in that case you can't do this because obviously in that case that B should be your, let's say, 2 cross 2 matrix or 2 cross 3 matrix, because your system is not your input is not a single one, it's a multiple input. So in that case, sorry, here M should not be there. So in that case, it is not possible for a multi input case. So we have already designed K from here. Now we need to design M. So let's say we design for the similar case, we have A equals to 0 1 minus 9 minus 1, B equals to 0 1, and C equals to, let's say, 1 0. Okay, so therefore my M equals to, first of all, first design this C A minus Bk inverse B, which is 1 0, and then 0 1 minus 9 minus 1 minus Bk 0 1, and this is minus 7 2, this inverse into B 0 1, right? So A minus Bk inverse, what is A minus Bk inverse? First of all, A minus Bk, what is A minus Bk? It's a 0 1 minus 2 minus 3. Therefore, A minus BK inverse is 1 by minus 3, 0, minus 1, 2. So what it would be? It would be minus 3 by 2, that means 1.5 minus zero point 0.5, yeah, 1 and 0. Okay, so therefore C A minus BK inverse B, what it should be 1 0 minus 1.51 minus 0.50 and 0 1. So it is 1 0 and 0.50. So it is minus 0.5. Okay. So M is minus 1 by C into A minus BK inverse into B, that is minus of minus 0.5, which gives you 2. Right. Now my system, if you take similar, if you take that is what is my system is now A BKX plus BR, sorry, BMR, and Y is equal to CX. So this is become now 0 1 minus 2 minus 3 X plus B into M. M is 2, so this is 0 2 R, and Y is equal to 1 0 X. So if now if you do the transfer functions, what would be the transfer function? So transfer functions would be your 2 by s square plus 3s plus 2. So now if you find out the steady state error at t tends to infinity, if you find out the, so s tends to 0, s into 2 by s square plus 3s plus 2 into 1 by s. So you will say, you will get this 1. That means my steady state error, this is my t. So my steady state error is 1 minus 1. This is 0. So that means we have to design this M. We basically here design this M to handle the steady state error part. And we have designed this K to handle the transient part. So this is one thing to approach. Okay. Now, in previous class, we have seen that we have talked about stabilizability. We have talked, we have said that the system, if the system is not fully controllable, the system is said to be a stabilizable. If the uncontrollable modes, those modes are uncontrollable, those states are uncontrollable, those are, if those are stable, then we can say the system is stabilizable. Okay, so for that case, we have not done any numerical on that part. So here we are going to design, we are consider a system and design that part. So let's say example 2. So my system state, I'm not going to write the, I'm just writing the A B matrices 1 1 0 0 1 1 and 0 0 minus 1, and B is 0 1 0. Okay. So for that case, first of all, we have to check the system is controllable or not. So for that case, we have to find out AB and A square B. What is AB? 1 0 0 1 1 0 0 1 minus 1, and then this is 1, this is 0, this is 0. Yeah. And A square B is basically A into AB, which is 1 1 0 0 1 1 0 0 minus 1, and this is B, AB, sorry. This is 1 0 0. So it is also 1 0 0. So the controllability matrix is basically B A B A square B, which is now become 0 1 0 1 0 0 1 0 0. So we have already know the how to find out the contributive matrix. So either you find the determinant or you do the row elimination process. So in that case, you do not need to do any kind of thing because you see that this column and this column, these two columns are equal. So in that case, we can already say, and also if you know go with the column part, you can already see that the end row is 0. That means there is a one row which is already a 0 row. That means the rank of the matrix is less than 3. So it is at least rank of the rank of matrix is 2 or less than, it is either 2 or less than 2. So you can see that it is only, the rank is only 2. That means there are two states which are, we can control the two state, and that means one state, because this is a 3 cross 3 matrix, so there are three states. So it means that two states are controllable, so we can design u for those two states. But there is a one state which is not controllable. That means our according to the system to be stabilizable, that which state is not controllable should be stable one. For that case, we need to design a similarity transformation matrix Q. So how we can design the similarity transformation matrix? So similarity transformation matrix, the design is very simple. So you have this observability matrix. Choose any two linearly independent vectors from here. So I am choosing, let's say this is the one vector and this is the another vector. Okay, 0 1 0 and 1 0 0. And since I need another vector to make this system, make this matrix square and as well as invertible. So I choose another vector which should be square and invertible, which makes this Q square and invertible. So I choose, let's say 0 0 1. This is my choice. Okay, you can choose 1 1 1 as well. That would be that choice is also okay if, as long as this Q matrix is invertible. Okay. So now we find out the Q inverse. So just to find the Q inverse. So it is 0 1 0 1 0 0 0 0 1. So its inverse is also the same, as you can see. So now we have to find out the similar matrix, which is Q inverse A Q, which makes the matrix basically this part 0 minus 1 1 1 2. Just a minute, just let me check. Yeah, 0 and 0 0 1, and B tilde is Q inverse B, which is 1 0 0. So you can see that should be minus 1, my mistake. So you can see this system, this 2 cross 2 reduced system is controllable, but this is not controllable. Okay, but the eigenvalue of this system state at the left half of the complex plane. So this is the stable one. That means system is stabilizable. Okay. So now my reduced system. What is my reduced system? So I'm not going to worry about this -1 part. I'm just worry about this x1 and x2 because I can control only this two state to reach to the desired position. I cannot control this point. And also I do not worry about this x state x3 because it is stable one. So eventually it will goes to the zero or goes to the desired point. So what is my reduced system? Let's say this is z dot equals to 0 minus 1 1 2 z plus 1 0, let's say u prime. So I need to design this u prime. So here my, and let the desired poles of this system, desired poles of this system is at, okay, so what is now alpha ds? It will be s square plus twice s plus 1. Okay, now controllability matrix BAB. So B is 1 0 and AB is 0 1. So it is 1 0 and 0 1. So identity C inverse is also identity. Using Ackermann's formula, what we can do? So using A equals to E transpose C inverse alpha dA. So I need to find out alpha dA, which is S square plus twice A plus I. So S square would be, just let me, S square would be 0. So S square is -1 -2 2 3 plus 2 into A. So 0 -2 2 4 plus 1 0 0 1. What it would be? -1 1 0 -2 -2 -4. This is 2 plus 2 4 and this is 3 plus 4 7 plus 8. So this is 0 1 1 0 0 1 0 -4 4 8. Right? So this is I, so you can ignore it. Just do 4 and 8. So this is your k tilde. This is k tilde for this reduced system. And since you are not going to, you are not able to control the last state, that is x3. So for that case, our final k tilde, let's say I'm telling it as a k1 tilde. So final k tilde is basically k1 tilde and 0, which is 4 8 and 0. Okay, now this is for reduced system, so we have to convert it into a real system because this we have already doing the we have done the similarity transformation, right? We have done the similarity transformation to find out the unstable modes. So we have to convert it into a original one. So k is equal to k tilde into q inverse. So after doing the k tilde into q inverse, you get 440. So this is this 440. So this 440, this is my original system where using this two term I can control the x1 and x2, and using, and we do not need any controller, we do not need any gain to control x3 because x3 is stable one. So this is my final system. So this is answer. Uh, so therefore the system is stabilizable. Okay. So up to that point, there is no issues, right? Is there any kind of issues? Then you can stop me and ask the questions. Okay. So move to the next segment. The next segment is we have already designed the that M matrix. We have already designed this M matrix using the to reduce the steady state error, right? Now instead of this M matrix, we can use the integrator. So it's basically so that means we have in previous we design u equals to minus kx plus mr. So here we design k and m. Now we design u equals to minus, let's say, kx minus kixi. Okay. So in MATLAB code, you know how to do this, all those things, right? I mean, there is a code called place. Using that, you can use, you have to give the desired location, like you have to provide A matrix, B matrix, and the desired pole location. So you will get the controller gain. Also, using Acker, there is a, I just use a note box over here. MATLAB command. So there is a command to find out k using place A, B, and let's say desired pole location. This is DP, desired pole location that I have given. Or you can use Acker, which gives you the Ackermann results. So normally in case of single input, single output system, if my system is a CISO system, we use Ackermann formula. If my system is a MIMO system, we cannot use Ackermann formula. Can anyone tell me why we cannot use Ackermann formula for MIMO system or multi-to multi output system? Yes, anyone can tell me why for MIMO system why we cannot use this Ackermann formula? Only we can only a CISO system we can use Ackermann formula. Can you tell me what is the reason? Okay, so let me tell you. Okay, no worries. Because you can see in Ackermann formula, where is that formula? So this is basically the Ackermann formula, right? So in Ackermann's formula, you see we have used this C inverse term, right? So this C inverse, to make it an inverse term, this C has to be a square one. So if the system is MIMO system, that is multi-input, multi-output system, in that case, that means if I have a multi-input, that means B is no longer a column vector. B will now become either a square matrix or rectangular matrix, whatever, depend upon the state and number of states and number of inputs. So that means if B, so here in case of SISU system, B is a only single vector. B is a single column vector. Okay, there's a B1, B2, dot, dot, dot. But in case of MIMO system, this B is now B11, B12, B21, B22, in that way, right? So to find controllability matrix, the first term is B, then AB, then A square B. So this C is no longer become a square one. The C will become a rectangular one, and we cannot find the inverse of a rectangular matrix, right? So for that case, when we are dealing with a CISO system, that is single out input, single output system, we can use this Ackermann formula. Once we move from single input, single output to multi-input, multi-output system, that is MIMO system, we cannot use the Ackermann formula. There are another formula that we have seen in the previous classes. We have seen another formula, that is similarity transformation, or there is other formula where we are comparing the desired characteristic equation with the A minus bk with the closed form characteristic equation, and from here we find out the k value. So there are separate formulas existed. So that's why whenever you are going to use the you are basically dealing with a MIMO system, you use place in you should use this place command in MATLAB, and should not use Acker command in MATLAB. Okay. Now move to the another part. So move to the previous part where we were. So just a minute. So in that case, so we use, this is the thing. So in that case, what would be our system block diagram? So let's say this is my integrator. I'm getting x from here. So this is x dot. So the b is over here. So there should be u, and here is a. So this is my x dot equals to ax plus bu. Now I multiplied this x with c, I get y, right? Now, what is in previous, what we did, we need a state feedback, right? That means we need a k over here. We need a k over here. But now we use, because this deals with the transient period. This is not dealing with the steady state period. To dealing with the steady state period, we need another controller. Okay. We need another controller, that is ki. So, so now we have two systems. First system is x dot equals to ax plus bu, and the second system is xi dot equals to r minus k. I did a mistake, sorry. It is directly y. This is not something. This is directly y. And ai is over here. This is minus and this is minus. Yeah. Okay. So r minus y. So this is r minus cx, right? So now my composite system is now x dot and xi dot equals to a0 minus c0 x plus b0 u plus there is 0 1 r. So this is my composite system. And now from here I have to find out the k. So this k, total k is basically k and ki. So this k and ki. So I have to find out this k now. So I am giving that my desired pole location. I'm going to give a desired pole location somewhere. Let's say S equals to minus P1 minus P2 and minus P3. I'm giving this desired pole location and using Ackermann's formula, because here you can see that the input is 1, so you can directly use the Ackermann formula, or if input is 2 or 3, based on that you use the place formula, or you use the normal simple formula, anything. You can find out the value of k, and we will see the my steady state error is reduced to 0. Okay. So this is very much similar to the previous examples. So I'm not going to give any example. This is just I am talk about this theory part. Okay. So now move to the state observer. So now, right now we have already considered everything that to design a state feedback controller, we have already considered that our all the system state, we can measure all the system state. I mean, there is a no problem in measuring. That means we can put sensor at every position where from where we can extract the system state, whether it's a internal or external. But in practical scenario, if you see, this is never happen. Okay, we cannot put sensor everywhere because some internal state is not reachable. It's not reachable in the sense it's not measurable. Like we cannot put sensor over there, or somewhere the situation is not situation is not according to our requirement that we can put sensor over there. If let's say if we put sensor over there due to some heat or some environmental condition, other environmental condition, or the system's other condition, the sensor may go may burn out, so we cannot get the actual result. So that means sometimes all the system state cannot be observable. We need to design an observer to extract those states, right? That's why we need to design this observer. The first strong condition to design this observer is that our system has to be observable. So that means, so let's say I have a plant something. So this is my plant. I am giving input to the plant and I am getting output. Okay. Now this output consists, let's say I have n number of state, but this output has m number of states or p number of states, which is less than n. So therefore, I need to design and state observer First, I'm going to discuss about the full state observer. Then I'm going to talk about the reduced state observer. So let's say this is a full state observer. Full state observer means irrespective of how many state we can measure, we are basically estimating every state. Let's say this plant has a 3 states, okay, or let's say this plant has a 4 state. So out of 4 states, I can measure the 2 states, and I need to estimate the 2 states, right? I can measure the 2 state directly from the sensor, and I need to estimate the other 2 states. But this full state, what this full state observer does, this full state observer does that this observer basically estimating all the 4 states, irrespective of how many states are measurable. This state observer estimate all the states. Sometimes it is not required because already the things that which we already measure, we can measure. Why need to estimate those states, right? So we will talk later. First, we talk about the full state observer. So this full state observer required the input, required the output, and then it gives the estimated state. Now this estimated state is used as a state feedback control to design a controller. And from here, I'm designing a control which use a state feedback controller, use as a state feedback controller, and then I'm giving this to the plant. That means we will see next. So now given my system is x dot equals to ax plus bu and y is equal to cx. Okay. So here x at 0 is 0. Let's say consider. Now the estimated the observer state. So the equation of the observer, the dynamics of the observer should be equal to the dynamics of the plant. It can't be different from dynamics of the plant because we are estimating the states. So that means we need same dynamics. Using the same dynamics, we are estimating the states. So observer equation is x dot equals to a x hat dot equals to ax hat plus bu and y hat equals to cx hat. So here in this case, this x hat 0 is not x0. It is x0 minus some epsilon. And our objective is to reduce this epsilon to 0, right? So up to that point, do you have any queries? So if not, then I'm moving forward. And if you have any queries, please stop me and ask me questions. Okay. So then what we should do? We should do that this y hat should approach y. Our output, the output of the observer should approach the output of the actual system state, right? So this means this c x minus x hat. So let's say we have changed this state. We are going to change this state as this format. Let's say a x hat plus bu plus some gain L into y minus y hat. So our objective should be this y minus y hat should be 0. So this should be 0. This should be our objective, right? And y hat equals to c x hat. So L is over here. L is a, here I'm considering the single input, single output system. So let's say L is like that, L1, L2, let's say up to Ln. Okay, depend on how many outputs are there. How many states are there? Sorry. So, estimation error xe of t is basically xt minus x hat t, right? So taking the derivative, we get x dot equals xe dot equals to x dot minus x hat dot. So this is x dot, which is ax plus bu, and x hat dot equals is basically ax hat minus bu minus l y minus y hat, right? So this be getting cancelled. So we get ax minus ax hat minus l into, convert into state format, c x hat. So we get a minus lc x minus x hat. So that means what we get? We get xe dot equals to a minus lc xe. This is what we got, right? So from here we can say, because what will be the solution? Solution of above equation. What would be the solution? It should be xe t equals to e to the power minus a minus lc t xc 0, right? This should be the, this is my solution of the above equation. So that means if the eigenvalues of this matrix, I think this should not be plus. This is so if the eigenvalues of this matrix lies in the left half of the complex plane, then our system, this state observer is asymptotically, I mean, we have designed the asymptotic state observer. Means our system state, our estimated state will definitely reach to the actual state asymptotically at t tends to infinity. This error will definitely goes to 0. So this error, our objective should be this error should goes to 0, and this will happen when the eigenvalue of a minus lc is negative, negative one, right? So that's why we need to design a L vector. Similarly, using Ackermann formula, there is a slight change in the Ackermann formula, or you can use the normal placement. Like, let's say, if I say that my observer gain or observer eigenvalue should lies in some p1 minus p1 minus p2. So from here you get the desired characteristic equation, and here you know that L1 a minus LC, you find out the characteristic equation using L1 L2 L3 and compare this both two, and you will find the L1 L2 L3 whatever. This is the one procedure. Another procedure is Ackermann's formula. So now in case of dual system, we have already read about the duality duality principle. That means if a system is controllable, its dual system is observable, or if the dual system is controllable, then my original system should be observable. We have already seen the duality. So in that case, so this is the error dynamics. We know the This is my error dynamics, right? A minus LC XC. This is my error dynamics. Now, for dual system, it's dual system, the error dynamics should be is XC, let's say tilde dot is my dual system. It should be A transpose minus C transpose L transpose XC tilde. Yeah, this is my dual system. So that means my AC is observable. That means my A transpose, if AC is observable, then we can find a solution of this. Like here we can find this A minus LC and put the value of L in such a way so that this all lies in the left half of the complex plane. So that means in case of dual system, this A transpose C transpose should be controllable. So this is basically the actual structure. So I'm going to discuss about one problem, a very short problem. Yeah. Example. So its system is given x dot equals to 0920 x plus 01 u and y is equal to 10 x. So here I am finding out. So the question is find out the full order observer. Sometimes you just ask that find out the observer. You have not mentioned that the question may not mention that full order. So if you have to find, if question answer, you just find out the observer such that the pole should lie in this and this location. So you have to find out the observer, full order observer. If the question specifically mentioned you have to find out the reduced order observer, then you need to find out the reduced order observer. Full order observer with desired pole location L1 equals to minus 10 and L2 equals to minus 8. Okay. So the first condition that we have to check is whether the system is observable or not, right? So for that case, you need to find out the C into A. So what is C? C is given as 1, 0 and A is given as 0, 9, 2, 0. So you will get 0, 9. So what is the observable matrix? This O is basically C, C, A. What is C is 1, 0. What is CA is 0, 9. So it is diagonal. That means O inverse exists. O inverse exists implies system is observable, right? Now here the Ackermann's formula is, so the Ackermann's formula that you need to memorize what is the Ackermann's formula. So I'm not going to discuss how this Ackermann's formula comes from. So you read any book, you will get to know that how this Ackermann formula comes from, how this Ackermann formula comes. So it is very much similar to the previous one, but slightly different. So Ackermann formula for observer is, let's say, L is my gain. So it is alpha D A O inverse E, right? So in case of controllability, it was E transpose C inverse alpha dA. So it is basically the transposed one. If you transpose it, you will get the E transpose O inverse alpha D. So if we make a transpose, that means the O transpose is basically the uh, C or the controllability matrix for the dual system, right? If you find out the dual system, if you find out, let's say I have find out the dual system. So in case of what is the duality principle, you can check the previous class or previous note, or the note that professor has given in the NPTEL. So you can see over here. So you'll see that dual system is controllable means the original system is observable. So dual system controllability and original system observability is similar. So if you take a transpose of this is basically the, you are basically finding out the controllability. If you just basically find out the feedback gain control for the dual system. If you take a transpose of this, so this is very much similar to the previous one. So what is our desired pole location? So desired pole location is given as s equals to -10 -8. Okay, so alpha d s is basically s plus 10, s plus 8. So it is s square plus 18, s plus 80. Okay, so now I have to find out alpha dA. For that case, that means it should be a square plus 18a plus 80i. So this is 0920 plus 180920 plus 80. So this is square. So this should be, this is 180018 plus this is 0 162 36 0 plus 80. It's 98 162 36 98. So this is my alpha dA. So I have find out the O. I know that O is 1009. So in case of diagonal matrix, the inverse, finding out inverse is very easy. This is basically all the diagonal elements are, you just put inverse on all the diagonal segments. So it would be 1001 by 9. Okay. And then what else I have? I have nothing. Uh, so it's 98, 36, 162, 98, 0, 1 by 9, and 0, 1. So here E is basically the vector. Similar to the previous case, E is basically the vector 0, 0, 0, last term is 1. The dimension should match the dimension of the O matrix. So it is 18 and 10.89. So this is my observer gain. So if we use this observer gain, then our system state, we can estimate the system state. So let me draw a block diagram and give a few facts of how to choose this observer gain and not. So let me first draw the block diagram. So, so this is my system original plant, that is x dot equals to ax plus bu. Okay. From this plant, I am getting x multiply with c, I am getting y, or put y little bit here, and I am giving u to the plant, right? This is u. So what now my observer dynamics is, this is my observer dynamics. So this type of observer is called a Leuenberger observer. State observer, I'm just writing it over here. So it is called, so this is my observer dynamic. This is x hat equals to a x hat plus bu plus l y minus y hat, right? So from here we can see that obviously u is the input to the observer as well, and you see that y and y hat. So from here I'm getting x hat. Let's say this is the output x hat that I am getting. Okay, this x hat, when this x hat is multiplied with a c, I will get y hat, right? So this is my y hat, and this y hat and this y, and need to be subtracted because we need to reduce the error. Okay, and now after subtracting it, it is fed to the observer. So this is the whole block diagram of the system state combined with the state observer. Now the logic is, because in a system we know that we have to design a controller, right? So as a control designer, we need to design a controller. But to design a control, we need to have the knowledge of all the states. Since we do not have the knowledge of all the states, we are designing a observer to estimate the states and design a controller. Okay. So that means we need to design controller and observer together, right? It's not a part that we design an observer only, we design a controller only. We need to design observer and controller together. So in that case, the controller gain, the controller poles, there is a slight, I mean, how to choose the poles of the controller and poles of the observer. According to our specification, according to our desired, according to our desire, how we'll choose the controller poles and the observer poles. Closed loop system, observer poles and closed loop system controller poles. The first need to remember that the first thing that you need to remember that we need that our observer should estimate the state as quick as possible, because if our observer can estimate the state as quick as possible, then we can design a controller, let's say k, because ultimately this k hat is multiplied, x hat is multiplied with k, right? Ultimately this x hat is basically multiplied with k, and this is basically the u that I am feeding to the system. So if we know all the state observer, we have, if we know all the system state, then instead of x we have only x hat. We have only instead of x hat we have only x. So that's why our our priority is that system observer should estimate the states as quick as possible. Once the system observer estimate the states quickly, we can design a feedback control law. So therefore, my observer poles should be the far in the left half side of the complex plane. Okay, and a controller pole should be should be nearer to the imaginary axis. Both should be in the left half of the complex plane, but observer pole should be the far most to the left than the controller pole. That means observer pole the observer should estimate the state as quickly as possible, because you see that here this is the system response. So let's say I'm just writing here as a not note, I will rub it after. So let's say eigenvalue of A minus LC is, let's say, minus lambda 1 minus lambda 2. I'm considering this 2 cross 2 matrix. Okay. So that means XET is basically e to the power minus lambda 1 t, e to the power minus lambda 2 t into XC01, XC02. So if this lambda 1 and lambda 2 is very high, that means the poles or the eigenvalues of the observer is very far of the left half of the complex plane, then this will decay to 0. This e to the power minus lambda 1 t and e to the power minus lambda 2, this will decay to 0 very fast, right? So that's why we need the observer pole should be at least 5 to 10 times than the controller pole. That is, our system, our observer should estimate the system state as quick as possible. Now, since I have already talked about the controller and observer controller form, right? So we are not basically design the observer single-handedly or the controller single-handedly for a system. So first, in case of a system, we need to design both accumulatively. I mean, we need to design together. Like here, the observer will do its work, and then my controller will do my other work. So then my controller will do the other work. Okay. So let's see. So we will going to see that is it possible that for a same system we can design the controller separately and design the observer separately, or it is required always it is required to design these two things together. So this is basically observer controller configuration. So in that case, we have assumed the first thing we have assumed this will be completely controllable and observable. So for original system, our PU, okay, so U is considered as a minus kx plus r. So it is a minus bk x plus br. Okay. Now y is equal to cx. Now observer dynamics. what is observer dynamics. So observer dynamics is x hat dot equals to ax hat plus bu plus l into y minus y hat. Since y hat is a cx hat, so it is basically, and b is equal to x hat plus b, put it over here, plus l cx minus cx hat. So it is a minus bk x hat minus lc x hat plus br plus lcx. Okay, so it is a minus bk minus lc x hat plus lcx plus br. So this is now my dynamics of the observer. So if we put it in a composite format, what it would be look like? So it would be look like a, this is minus bk, this is lc, and this is a minus bk minus lc x hat plus b and b. This is r. So this is the overall state space representation of controller observer configuration. Now, this, so what is our objective? Our objective is this whole system should be asymptotically stable. So the objective is the above system should be asymptotically stable. So for that case, what should be our requirement? We have already studied in the stability part that for a system x dot equals to ax plus bu, or for a system x dot equals to ax, so this system should be stable if the eigenvalue of a matrix or eigenvalue of the system matrix should lie in the left half of the complex plane. That means the eigenvalue of this matrix should lies in the left half of the complex plane. Okay, so for that case, what we can do, let's say, so, how we find out the eigenvalue. I'm just, let's say, I'm giving another name to this whole system is, let's say, a cursive A. Okay, this matrix. So how, what is the procedure to find out the eigenvalue? It's basically determinant of Si minus this cursive A, right? So here we are going to see that whether K and L, the controller and the observer gain, can be designed separately or not. So this is the determinant. So that means this determinant is basically determinant of this matrix, right? Which is Si minus A bk, and here minus lc, and here Si minus A plus bk plus lc, right? This is the term. Now we have already studied the row exchange method, row elimination method, right? So what we'll do, we add this to that and then subtract. Okay, so let what is I'm just doing this is first. Let me do it in that way. So this is Si minus A matrix. This Si minus A matrix is Si minus A minus LC Bk and Si minus A plus Bk plus LC. Row elimination method, row or column. So what we do the C2 prime is C1 plus C2. So what we'll get Si minus A minus LC Si minus A plus Bk and here Si minus A plus Bk. And now what I will do? I will do row 2, sorry, row 1 is row 1 minus row 2. So what I will get? This is Si minus A minus LC plus LC. This is 0. This is minus LC. And this is Si minus A plus Bk. So as you see, this is basically a lower triangular matrix. This is lower triangular matrix. So we know that in case of a lower triangular matrix or upper triangular matrix or diagonal matrix, the eigenvalues lies in the diagonal. That means the determinant of Si minus A plus LC is basically determinant of Si minus A plus LC into multiplied with determinant of Si minus A plus Bk, right? So that means we can design the controller gain and observer gain. We can design the controller gain and observer gain separately. But keep in mind, whenever we choose the eigenvalues of the observer, that should be the 5 to 10 times larger than the eigenvalues of the controller. Okay, just to make sure that our system state should be estimated as quickly as possible. So for that case, so here we can say that our system we can design our the observer gain L and the controller gain K separately. It is not required to design these two things combined. Okay. So up to that point, does anyone have any queries? Uh, you can ask me, or we move to the last segment, which is a reduced order part. So the I'm not going to give any kind of example for that case because you have already seen how to find out the L, that is observer gain. You have already seen in the examples. I have already shown you the examples of how to solve the how to find out the controller gain and how to find out the observer gain. So you just do the same techniques. Choose a system and you just design a controller. Let's say you design a controller so that our system closed loop system state should system pole should lie in -2, -1, -2. And similarly, you design an observer gain for the same system so that the observer pole should lie in, let's say, in -5, -10. So you just design these two things separately. Use Ackermann formula if you're using the CISO system. Use Ackermann formula, or if you using the MIMO system, you use different formula. You will definitely find out the value of L and C, and you will see that your system can estimate the state properly, and your system can control the state properly. Okay. Now the reduced order system. Sorry, reduced order observer. So reduce order observer means we already. So, do you have any kind of questions, Puneet or the other and Mr. Puneet or SS Kulkarni? Do you have any other questions regarding the whatever I have talked about, or is it clear to you?
No, sir.
Is it clear, right?
Yes.
Okay, okay. Thank you. So, in reduce order observer, so as I've already said that we cannot measure all the states, but we can measure few states. Let's say if I have a system with a x equals to x1, x2, x3, so we measure these two states are measurable, but this is not measurable. So here in previous problem, we have seen that depend on the whether the system state is measurable or not, the full state observer is basically estimating all the states. It is the observer is basically estimating all the states x1 hat, x2 hat, and x3 hat. But this is not required, right? This is basically the this is basically unnecessary. We are estimating x1 and x2 because we are already measuring this. So what is the requirement? So now reduced order says that, okay, I am not going to estimate x1 and x2 because this is already measurable. I am just going to x3 hat. Instead of measuring x1 and x2 as well, just forget about it and just measure the x3 hat. Okay. So here, so you have a system like that. X dot equals to ax plus bu and y is equal to cx. Y is equal to cx. Okay. So now we define a similarity transformation matrix. How to define similarity transformation? Let's say I'm calling it as a P. Let's say this is C and C hat. So this C is this C. This is basically this C. And we have to make this C hat in such a way so that our P is non-singular. Okay. So once we find out, so what would be the system is, let's say X is equal to X bar is equal to P of X. Okay. So therefore, A bar is equal to PA, P inverse, B bar is equal to PB, and C bar is equal to P inverse. So after doing this, let's say you get this kind of structure. So here, this is looks like a 2 cross 2 matrix, but let's say x1 belongs to Rp. That means x1 represent the p number of states, x1t represent p number of states and x2 belongs to Rn minus p. The total system's dimension is n. There are n number of states is there. So x1 is the p number of states and x2 is represent n minus p number of states. Okay. So that means you can see that x1 is measurable. X1 is measurable, or you can say it is known, where x2 is not measurable. That means unknown. So we have to design a reduced order observer for that case. Okay. So what is the x1 dot formula? It is a11 x1 plus a12 x2 plus b1 u. Okay. And x2 is a21 x1 plus a22 x2 plus b2 u. Right. And let's say y tilde, I just call it a tilde, y tilde is only x1. Call it a z. Wait, it will be better. Z is the x1. So this is equation 1, this is equation 2. To rewrite equation 2 is x2 is unknown. So I just put all x2 in this format and we know the x1 and u, right? We know that x1 and u. Okay. So this is basically a22 x2 plus, let's say, b tilde u tilde. I'm just calling this, I'm just calling this term as a u tilde and this term as a b tilde. Okay. So now consider this y tilde here is x1 dot minus, or don't call it a y tilde. So in this equation, sorry, in this equation, we don't know this term, right? So we put this term aside. So a12 x2 is basically x1 dot minus a11 x1 minus b1 u. Okay. So we have already collect all the things. We need to design x2. We need to estimate x2. So for that case, what is the observer dynamics? The estimation of x2 is x2 hat. So observer dynamics, we have seen in the previous, we have seen just previously that x2 hat dot should be the same dynamics as x2 a22 x2 plus b tilde u tilde plus some, let's say, l tilde into, if we call it as a, let's say, y tilde minus a12 x2 hat. So this is basically output equation. This is the dynamics equation. This is the dynamics equation. This is basically the output equation. Okay. So our error should be, this should be hat. So this is just write all those things is a12, sorry, a21 x1 plus B1U, this term, plus L tilde. What is y tilde? It is x1 dot minus A11 x1 minus B1U minus A12 x2 hat. So what is, we get A22 minus L tilde A12 x2 hat plus A21 x1 plus B1U. What is this term? This term is basically A12 x2, right? So this is L tilde A12 x2. Now we have to take a error, that is x2e equals to x2 minus x2 hat dot equals to x2 dot minus x2 dot hat. So this is basically A22 is A22 x2 plus A21 x1 plus B1u minus A22 x2 hat minus A21 x1 plus B1u minus A L tilde. Sorry, I just made a mistake. A12 x2 hat. This is A12 x2. So this term cancel out. So this is basically x2e dot is equal to A22 minus L tilde A12 x2e. So what is similarly again? We need this term, the eigenvalue of this term should be in the left half of the complex plane. Then how, just like the same way we design an observer full order, we have to design this. Okay. So I hope it is clear to all of you. Okay. So eigenvalue should lie in the left half of complex plane. So this is about all about today's discussion. So today already. So if so, I'm just last time I'm asking you, is there anything that you want to ask? You can ask. And since our course has been completed today, and last, yeah, Puneet, I think you have something to say.
I just wanted to ask
Could you please speak loudly? Could you speak loudly? Uh,
am I audible now?
yeah, you are audible now.
So I just want to just have a curiosity to know that whether during the exam we will be having the access to MATLAB or not.
Uh, I don't think that, I literally don't know whether they will give any access to MATLAB or not. I have no idea. Uh, Most probably, as far as I know, that I don't think they will provide any kind of MATLAB access, but I'm not sure about that. So you just put a you just ask to the NPTEL team regarding this. I'm sorry that I'm not able to answer this question. Yeah.
Because most of the things practice that I have done during this
Yeah.
course is using
Okay.
MATLAB. How to get those things. I think the lectures and the lectures which sir has provided is very nice. But how
Yeah.
to get it transferred into MATLAB and how to calculate using MATLAB is another uh, one thing which we need to discuss.
Okay. So what do you want to discuss about? I mean, so you need to discuss how we use this MATLAB code, right?
It's MATLAB code or how can we, it's like just now we discussed that eigenvalue like a complex plan, what we discussed right now. So how can
Hmm.
we implement using MATLAB also, or that is,
Okay. So for that case, you can tomorrow at 3 p.m. to 5 p.m. I'm going to take the extra session class. Okay, if you wish to join, you can join over there, and we will discuss over how we can do this MATLAB code thing. Or here, I have already told you that
Yeah, yeah.
for that case, uh, in that case, that MATLAB code that you can use as place and acre, right? So
Correct.
this is the two commands that is available in MATLAB, and that is for, you can say, that is for find out the controller gain. So as I've said that you can also use it to find out the observer gain. So in that case, what you should do for observer gain, what you as I've said that a system is controllable if its dual system is observable, right?
Yes, correct.
So in that case, what you can do, the place command instead of uh,
You discussed about
eight,
acre and tensor, right?
yeah,
So I tried acre works for both CISO as well as MIMO.
acre works for.
Both CISO as well as MIMO.
I'm sorry, your voice is sometimes
CISO,
breaking. And
yeah,
ha
single input.
single input.
CISO as well as MIMO both. Multiple input, MIMO plant.
For Mimo plant case, your acre is working. You are
Correct.
saying that, right?
Yes.
So
So
look, I don't know. Let me check, because as far as I have said that in Mimo system, your C matrix, the controllable matrix, is not no longer become no longer a square matrix. It is become a rectangular matrix. So
I got
in
your point.
uh,
Yeah. But
okay,
that's correct.
so then okay, if you wish, you can join the tomorrow extra session class. In tomorrow extra session class, we will discuss whatever the queries you have from week 1 to week 8, and we will discuss about all those MATLAB codes, because we have a 2 hour session, so we can discuss this over there, right?
Okay. Thank you
Okay,
so much.
okay.
But
Yeah.
whether we have to use there the calculators, it will be available
So
on the
cal
onboard this, or can we
uh,
use our own? Means the our
I think
calculator is
uh, I think you can use your own calculator. I don't think there will be any issues. I mean,
Calculator, I think they have given a link for a scientific calculator
okay, they will give a link for a scientific calculator. Okay, then
that you can
because
use.
okay, so because obviously in modern calculators you can multiply your matrix up to like 4 cross 4, 4 cross 4 or 3 cross 3. I don't remember. So it is very easier to do all those things. That's why they may be provide a scientific calculator by their own. So I'm not sure about, I mean, what are the procedure of the final exam. So it's better if you ask these questions to the NPTEL team. They will give you a proper answer. I'm just a TA just to give doubts regarding this course. So if you have any doubt, then we can discuss. Otherwise, I'm just wrap it up. And tomorrow in extra session, using the same link, you can join. Tomorrow in extra session, we can discuss the whatever the problems in previous weeks as well. Okay.
So, thank you.
Okay.
now. Can you share these videos which you have taken in these problems? Can you share
All the
till
videos,
the
yeah, I have already shared all the videos, and I think you can check it from NPTEL website, right? You can access all the. I have already shared the Google Drive where you can get the all these notes, where you can get all this all my numericals and the videos as well. YouTube link is already shared with you. I think you can get it from NPTEL website. They have, once you go to the NPTEL website, you will see that there is a let me check just a minute. Yeah, you can go to the problem solving session recording, and if you click here over there, you can see all those recordings. You will see the an Excel sheet, a spreadsheet. So the links is provided over there. There, because here the two TAs of this, I'm the Rudrashan. And there's another trace which is Srishti Siddharth. Yes, so you can go and check any YouTube links or any Google Drive to access this all the notes and questions. Okay. Okay. Hello.
Do we have any material? Yeah. Do we have any material for the course for the exams questions or somewhere we can?
Material, I would say that you just see the Ogata book, or you can see the Anstackley's book. I mean, I don't know what professor. I think in this no in this course, I think professor had provided professor had mentioned the book of Ogata. I think so. You can
Yes.
go and Ogata book is very good. That is a very good book. And other books. Let me check what are the books they have mentioned.
My question is, since we have very only 6 7 days left, so where
I
we
think
have some
Ogata book
entire.
is yeah, Ogata book is very. I mean, you can go through the examples or the questions or the whatever the examples and the exercise questions. I think that is a very good book for state feedback control, feedback of sorry, state observer, and all those things. Stability part. Uh, because this part as far as matlab, my concern is like first 1 2 weeks, that is a companion form, controllable, canonical and diagonal, these are very easy. Then the stability and state feedback control, pole placement, these are a little bit difficult. So I think Ogata book is the very good book. I mean, you can find a various type of very questions and examples, so you can go and check that.
Sure.
Okay.
Thank you
Yeah.
so. Thank you so much.
Okay, okay, thank you. So, okay, then I'm stopping this recording. Thank you. So you can leave.